Welcome to the Deep Dive. This is the place where we really get into the nitty-gritty of crucial economics concepts and, well, make them make sense. I'm Adam.
And I'm Grace.
We're both proud educators from School on X.
That's right. And today we are tackling really the engine room of microeconomics. It's the theory of consumer behavior.
It really is. It's one of those topics that once you get it, you see it everywhere.
Oh, absolutely. It explains basically every choice you make, you know? The clothes you pick, the snacks you buy, even bigger things like college choices. Let's start with a little puzzle, shall we?
Okay, I like puzzles.
Why did you choose that specific brand of coffee this morning? Or maybe why coffee at all? Why not tea or just save the money and drink water?
See, that seems like such a tiny decision, doesn't it? But in economics, it's huge. That's the core of it all. The problem of choice.
Exact.
Every single one of us, every rational consumer, and that includes you listening, faces this. We have, well, basically unlimited wants, right?
But, and it's a big but, we have limited resources, we've only got so much money, our income is fixed, and the things we want have prices attached. Fixed prices.
Precisely. So economists trying to model this, they have to look at these two sort of different worlds crashing together.
Right. The first world is all about desire. What do you like? What brings you satisfaction or happiness? That's preferences.
Preferences, satisfaction, utility, that whole internal world. And then the second world, that's reality.
What can you actually afford? That's your budget, your income, the prices in the market.
So our mission today in this deep dive is to explore the two big ways economists have tried to model this balancing act. We'll start with the older idea, cardinal utility analysis.
The numbers game, you could call it.
Yeah, exactly. And then we'll move to the more modern and I think more realistic ordinal utility analysis.
Which is more like a ranking game. It's going to be fascinating.
Okay, let's jump into that first one. Cardinal utility. It's kind of like a history lesson to start, isn't it?
It really is. You have to imagine a time when economists actually believed, or at least theorized, that they could put a number on happiness, like literally measure satisfaction. That's the core idea of utility.
Utility itself is a simple enough concept. It's just the power a thing has to satisfy a want. If you're really thirsty, water has incredibly high utility for you at that moment.
Right. But the cardinal part, that's the tricky bit. The key assumption here was that you could measure this utility in numerical units. They even called them utils.
Utils. It sounds a bit funny now.
It does. But the idea was you could say, okay, this chocolate bar gives me 20 utils of satisfaction, or buying this new shirt gives me 50 utils, like measuring temperature in degrees.
It feels pretty unrealistic when you put it like that.
Oh, definitely. But the framework it created is still super important for understanding the basics. And we have to remember, even in this hypothetical world, utility is deeply personal. It's subjective.
That's a key point. My utility for, say, a fancy new video game might be sky high, like 100 utils. But for someone who doesn't play games, maybe 0 utils or even negative if they think it's a waste of time.
Exactly. And it's not just subjective, it's also contextual. This is vital, especially for grade 12 students thinking about exams. Utility isn't stuck to the good itself. It changes based on time and place.
Give us an example.
Okay, think about a really warm, high-quality room heater. What's its utility in, say, Ladakh during the dead of winter?
Immense. Potentially life-saving utility. Very high utils.
Right. Now, what's the utility of that exact same heater in Chennai during the hottest summer month?
0. Or maybe even negative, because it's just taking up space you could use for a fan.
Precisely. Utility isn't fixed. It depends entirely on the circumstances. It's dynamic.
Okay, so if we're imagining measuring this stuff, we need some specific concepts. Let's talk total utility versus marginal utility.
Right. Total utility, TU, is, well, exactly what it sounds like. It's the total satisfaction you get from consuming all the units of a good up to a certain point.
So if I eat 3 slices of pizza, the TU is the combined happiness from slice 1, slice 2, and slice 3. It adds up.
Exactly. It depends directly on the quantity you've consumed. But the real analytical power, the concept that drives everything, is marginal utility.
Marginal. That word pops up everywhere in economics. It always means extra or additional.
Always. So marginal utility is the change in your total utility when you consume just one more unit of the good. It's the satisfaction you get from that very last unit you consume.
Okay, let's make that concrete. Forget the formulas for a second. If eating, say, 4 cookies gives me a total utility of, let's say, 28 utils,
Okay.
and then I eat a 5th cookie, and my total utility goes up to 30 utils, what's the marginal utility of that 5th cookie?
It's simply the difference. You went from 28 to 30 by adding that one cookie. So the MU of the fifth cookie is $30.28, which is 2 utils.
Just 2 utils. Much less than the first cookie probably gave me.
Almost certainly. And this relationship works both ways. If you know the MU of each cookie, the first, the second, the third, and so on, up to the nth cookie, you can just add all those marginal utilities together.
And you get the total utility for n cookies.
Right.
TU is the sum of all the MUs.
Exactly. TU is MU1 plus MU2 plus MU plus MU. The total is the sum of the increments.
This step-by-step, unit-by-unit thinking is what allows economists to formulate probably the most important psychological law in this whole area, the law of diminishing marginal utility, LDMU.
Yes. This is absolutely fundamental. It basically captures a core aspect of human experience when consuming things.
So what's the core idea? Lay it out for us.
The law states that as you consume more and more units of a specific commodity, holding your consumption of other goods constant, the additional satisfaction, the marginal utility you get from each extra unit will eventually decline.
It has to, right?
Right.
Your desire gets less intense as it's satisfied.
Precisely. You start getting full or bored or just less excited.
Yeah.
Satiation sets in.
It's why the first bite of chocolate cake is amazing, the second is great, the third is good. But by the 10th bite, if you even get there, it's probably not adding much happiness at all.
Let's trace that pattern with some numbers, like in the textbook example. Maybe the first unit of something gives you 12 MU.
Okay, high satisfaction.
The second unit gives you, say, 6 MU. Still adds satisfaction, but less.
Right.
The third gives 4 MU. The fourth gives 2 MU. Notice what's happening to total utility. It's still going up. 12, then $12 plus 6 equals $18, then $18 plus 4 plus 4 to 4, so 2, then $22 plus 2 equals 2, 4, 2.
Yeah, TU is increasing, but it's increasing by smaller and smaller amounts each time. The rate of increase is slowing down.
Exactly, because the MU is diminishing. This leads us to a really important point in consumption. The point of satiety.
Satiety, meaning you're full, you're satisfied.
Right. This is the point where the marginal utility of the next unit becomes 0. Consuming one more unit adds absolutely nothing to your total satisfaction.
So in our example, maybe the fifth unit has an MU of 0, the TU stays at 24, you've hit the peak.
You've hit the peak. Your total utility is maximized right there. But what happens if, for some reason, you consume another unit after that, say a 6th unit?
Then it probably starts getting unpleasant, right? Like eating way too much.
Exactly. The marginal utility becomes negative. Maybe the 6th unit has an MU of numerical 2. It actually reduces your total satisfaction. Your TU would fall from 24 down to 22. You've gone beyond satisfaction into discomfort.
Okay, this LDMU makes intuitive sense. But how does it connect to the real world? You mentioned businesses.
Ah, yes. Think about businesses that rely on you consuming a lot, like an all-you-can-eat buffet.
Okay, yeah. How does LDMU explain those?
Buffets work because of LDMU. The restaurant sets a price knowing that your marginal utility for the, say, 10th plate of food is going to be incredibly low, maybe even 0 or negative.
Right. They're betting that you'll get full and stop long before you eat enough to make the price unprofitable for them.
Precisely. If LDMU didn't exist, if that 10th plate gave you the same massive satisfaction as the first plate, everyone would eat until the restaurant went bankrupt. Rational consumers would just keep going.
That makes sense. What about something like streaming services? Netflix, for example.
Same principle. Once you pay your monthly fee, the marginal cost to you of watching one more movie is essentially 0.
True. It doesn't cost extra per movie.
But your marginal utility of watching the 5th hour of TV in a row is definitely lower than the first hour, right? LDMU kicks in. They know you won't physically watch 24/7, even if the marginal cost is 0, because the marginal benefit utility drops off.
Okay, got it. So LDMU is real. It affects business models. But you said it's foundational for something else really big in economics.
Yes, the absolute cornerstone application. LDMU provides the logical underpinning for the law of demand.
The law of demand. That's the one that says when price goes down, quantity demanded goes up and vice versa. That classic downward sloping demand curve.
That's the one. But why does it slope down? LDMU gives us the answer.
How so?
Think about it. Since each extra unit of a good gives you less satisfaction, lower MU than the previous one, a rational consumer will only be willing to buy that extra unit if the price is also lower.
Ah, right. If the first ice cream cone was worth, say, 50 rupees to me because the MU was high.
Exactly.
The fifth ice cream cone, with its much lower MU, is definitely not worth 50 rupees anymore. I'd only buy it if the price dropped significantly. maybe to 10 rupees.
Precisely. Your willingness to pay for additional units decreases as your marginal utility decreases. And it's this decreasing willingness to pay that directly creates the downward slope of the demand curve. People buy more only if the price falls, because the value they get from extra units is falling.
Okay, so cardinal utility, measuring utils, gives us LDMU and helps explain the law of demand. But we already agreed measuring satisfaction numerically is, well, a bit unrealistic.
Deeply unrealistic, which is why economists moved towards ordinal utility analysis. This was a major shift. It recognized that people don't need to assign numbers to satisfaction. They just need to be able to rank their preferences.
Rank them, meaning?
Meaning you can say, I prefer this combination of goods, bundle A, over that combination, bundle B. Or you might say, actually, I'm equally happy with bundle C and bundle D. I'm indifferent between them. It's about comparison and ranking, not measurement.
Okay, that sounds much closer to how people actually make decisions. So what's the main tool used in this ordinal approach?
The central tool, and probably one of the most important diagrams in microeconomics, is the indifference curve, often just called an IC.
Right. Indifference curves. Let's define that clearly. What is an IC showing us?
An indifference curve is a line on a graph that connects all the different combinations or bundles of two goods, let's stick with pizza and soda, that give the consumer the exact same level of total utility or satisfaction.
So every single point, every combination of pizza and soda that lies on that specific curve makes the consumer equally happy.
Exactly. They are literally indifferent between any of those points. If point A, maybe 1 pizza, 10 sodas, is on the curve, and point B, maybe 2 pizzas, 5 sodas, is also on the same curve, the consumer gets the same total satisfaction from A as they do from B. They wouldn't mind which one they got.
Okay. And these curves, they always seem to slope downwards from left to right on the graph. Why is that? Why the downward slope?
That downward slope is essential, and it comes from a basic assumption we make about preferences called monotonic preferences.
Monotonic meaning?
It just means more is better. We assume consumers prefer bundles with more of at least one good and no less of the other. So if you're on an indifference curve and you get more of one good, say more pizza as you move rightwards, you must give up some of the other good, soda, to keep your satisfaction level the same.
Ah, I see. If you got more pizza and didn't give up any soda, you'd have more of both. And that would have to make you happier, right? You'd jump to a higher indifference curve.
Precisely. To stay on the same level of happiness, gaining one thing requires sacrificing another, hence the downward slope.
And the slope itself, the steepness of that curve at any point, that has a special name too, doesn't it?
It does. The slope of the indifference curve tells us the marginal rate of substitution, or MRS.
Marginal rate of substitution. Okay, break that down. What is it measuring?
The MRS measures the rate at which the consumer is personally willing to trade off one good for another while staying on the same indifference curve, meaning while keeping their total satisfaction constant. It's your internal subjective trade-off rate.
So it's not about market prices yet. This is purely about my personal feelings.
Purely psychological at this stage. It asks, how many units of good Y, say sodas, are you willing to sacrifice to get one additional unit of good X, pizza, and feel neither better nor worse off?
Okay. And the calculation is based on the changes.
Right. It's the absolute value of the change in the good on the vertical axis, the one you're giving up, delta Y, divided by the change in the good on the horizontal axis, the one you're gaining, delta dias. So MRS, delta Y, delta X. It tells you how many Y you trade per unit of X.
Now, just like we had the law of diminishing marginal utility driving the cardinal approach, is there a similar law here for the ordinal approach?
Yes, absolutely. The shape of the standard indifference curve is determined by the law of diminishing marginal rate of substitution.
Diminishing MRS. Okay, what does that mean intuitively?
It means that as a consumer gets more and more of one good, say good X, pizza, the amount of the other good, good Y, soda, they're willing to give up to get one more unit of X decreases.
So the more pizza I have, the less soda I'm willing to sacrifice for yet another slice of pizza.
Exactly. It mirrors the LDMU logic. When you have lots of X and little y, X is less valuable at the margin and Y is more valuable, so your willingness to trade Y for X diminishes.
Let's use that mangoes and bananas example again. If I start with 15 mangoes and only one banana.
That one banana is precious.
Right. I might be willing to give up, say, 3 mangoes just to get a second banana. My MRS is high, 3.1.
Okay. Now, imagine later you've got, say, 5 mangoes but 10 bananas. Bananas are plentiful now, mangoes are scarcer.
To get an 11th banana, which isn't that exciting anymore, I might only be willing to give up maybe half a mango Or let's say 1 mango to keep it simple. My MRS has fallen to 1.1.
Perfect. You value the remaining mangoes more and the extra banana less. Your willingness to substitute mangoes for bananas has diminished.
In this diminishing MRS, what does it do to the shape of the indifference curve on the graph?
It's what makes the standard indifference curve convex to the origin. It bows inwards towards the 0 point on the graph. That curve gets flatter as you move along it to the right, reflecting the falling MRS.
Convex to the origin.
Okay.
But are all indifference curves like that? What about goods that are, like, perfectly interchangeable?
Good question. No, not all curves are convex. We have the special case of perfect substitutes.
Perfect substitutes, like...
2 different brands of bottled water that taste identical to you. Or the classic textbook example, 5 rupee coins and 5 rupee notes. Assuming you only care about the monetary value, they are perfectly interchangeable.
Right. If I have a 5 rupee coin, I'm always willing to swap it for 1 5 rupee note, and vice versa. Doesn't matter how many coins or notes I already have.
Exactly. Your willingness to substitute is constant. The MRS between them is always 1.1 or whatever the fixed ratio is. It doesn't diminish.
So if the MRS doesn't diminish, what does the indifference curve look like for perfect substitutes?
It's not convex anymore. It's a straight line sloping downwards. The constant MRS means a constant slope. That's a key difference to spot.
Okay, straight line for perfect substitutes. Convex curve for most regular goods due to diminishing MRS. Now, one consumer usually has lots of these curves, right? Representing different levels of happiness.
Yes, the whole collection of a consumer's indifference curves is called an indifference map. It's like a topographical map of their satisfaction levels.
And we rely on that monotonic preferences idea again here, don't we? The more is better rule.
We do. Monotonicity tells us that any indifference curve that is further away from the origin, higher up and to the right, represents a higher level of satisfaction, because bundles on that higher curve have more of at least one good.
So consumers always want to reach the highest possible indifference curve on their map.
That's the goal. Higher curves mean more happiness.
This logic leads to a really important rule about indifference maps. 2 indifference curves can never cross or intersect. Why not? What goes wrong if they do?
The non-intersection rule. It's crucial because if they did intersect, it would lead to a logical contradiction, violating our basic assumptions about preferences.
Okay, walk us through that contradiction. Let's say 2 curves, IC1 and IC2, somehow cross at a point, maybe point A.
Right, so point A lies on both IC1 and IC2. Now pick another point, B, that lies only on IC1, and pick a third point, C, that lies only on IC2.
Okay, got it. A is on both, B is on IC1, C is on IC2.
Since A and B are on the same indifference curve, IC1, what does that mean about the consumer's satisfaction?
They must be equally happy with A and B. Satisfaction A, satisfaction B.
Good, and since A and C are on the same indifference curve, IC2.
Same logic. They must be equally happy with A and C. Satisfaction A.
Now, basic logic, if A equals B and A equals C, what must be true about B and C?
Well, then B must equal C in terms of satisfaction. Satisfaction B. Satisfaction C. The consumer should be indifferent between bundle B and bundle C.
That's what the intersection implies logically. But now, let's look at where B and C would be on the graph if IC1 and IC2 intersected. Because they are on different curves, except at point A, one of them, say B, must be further out from the origin than C, containing more of at least one good.
Right. If B has, say, the same amount of pizza as C, but more soda, then our more is better rule. Monotonicity kicks in.
Exactly. Monotonicity demands that the consumer must prefer bundle B to bundle C because B has more soda. Satisfaction B.
Satisfaction C.
So, wait, the intersection logically implied B in satisfaction, but monotonicity implies B, C in satisfaction. We have a direct contradiction. Bang! The system breaks down. You can't have both indifference and preference between B and C simultaneously. The only way to avoid this contradiction is if indifference curves never intersect in the first place. It's a neat piece of internal consistency in the theory.
Okay, we've mapped out the world of desire with indifference curves. We know the consumer wants to climb as high up that satisfaction map as possible. But now, reality bites.
Indeed. You can desire the fanciest bundle on the highest possible indifference curve, but you're always limited by your wallet. This brings us to the budget constraint.
The constraint. So we assume 2 key things are fixed here, right?
Yes. We assume the consumer has a fixed amount of income, which we usually call dollar for money income, over a given period. And they face fixed market prices for the goods they want to buy. Let's call them P dollars for good 1 and P dollars for good 2.
And the basic rule is simple. You can't spend more money than you have.
Can't spend more than $. So the total amount you spend on good one, which is its price, P.1 times the quantity, 6 by $1, plus the total amount you spend on good two, P22 times 6 by $, must be less than or equal to your income, 1.
That
$5 times 3 plus 5 times 3 plus 15 plus 15 plus 15 was $30. That's more than your 20 rupees income.
So 3 is unaffordable. It's outside the budget set.
Exactly. The budget set includes bundles like 0, 0, 1, 2, $1, 0, 3, 2, 1, 1, 3, 4, 3, 1, 3, 1. All those add up to 20 rupees or less.
Now, the bundles that cost exactly the income, like 1, 3, and 2, 2, and 4, 0, 4, they form the outer edge of this budget set, right?
Precisely. That outer edge is called the budget line, BL. It represents all the bundles where the consumer spends their entire income. The equation for the budget line is P1 by $1 plus P2 by 2 equals M.
So the inequality gives the whole budget set the line and the area below it, while the equality gives just the budget line itself.
Perfect. And this budget line is crucial graphically. We can draw it easily using its intersect.
The intercepts where it hits the axis.
Yeah. If you spend all your income only on good one, how many units can you buy? You can buy them all or PM1 units. That's the horizontal intercept, where the budget line hits the x-axis, good one axis.
Makes sense. And if you spend everything on good two,
you can buy $1 P22 units. That's the vertical intercept, where the line hits the y-axis, good two axis. Connect those 2 points, and you've got your budget line.
and the slope of that line. That's important too, right?
Very important. The slope of the budget line is Winabo 22222. The negative sign just shows it slopes downward. But the absolute value, P$P22, that's the key number, is called the price ratio.
The price ratio, P$P22.
What does that tell us?
It tells you the rate at which the market allows you to substitute good one for good two. It's the objective trade-off dictated by prices.
So if P$1 is 10 rupees and P$2 is 5 rupees, the price ratio, P$P2, is 105 equals 22. What does that 2 lot mean?
It means that in the market, to get one more unit of good 1, which costs 10, you must give up 2 units of good 2, since $2 times 5 equals 10 times.
Okay.
The market forces you to trade 2 units of Y for 1 unit of X. It's the rate you're able to substitute, based purely on prices.
Okay, that's distinct from the MRS, which was the rate I was willing to substitute personally. This is the market rate. Exactly. Keep those 2 distinct MRS, willingness versus price ratio ability.
Now let's see how this budget line shifts or pivots when things change. This is super important for understanding demand later.
Right. What happens first if my income changes but prices stay the same? Say I get a raise.
If your income increases, you can obviously buy more of both goods. Both intercepts, MP101 and MP22, will increase. The whole budget line shifts outward, parallel to the old one.
Parallel. Why parallel?
Because the prices P21 and P22 haven't changed. So the slope, which is P21, P22, remains exactly the same. The line just moves further out, expanding your budget set.
And if my income falls, same logic, it shifts inward, parallel.
Yep, parallel inward shift. Your affordable choices shrink, but the relative price trade-off, the slope, is unchanged.
Okay, that's income change. What about a change in the price of just one good? Say, the price of good 1 goes up, my income dollar and the price of good 2 stay the same.
Ah, now the slope does change. A price change for one good causes the budget line to pivot or rotate.
Pivot. Around which point? It pivots around the intercept of the good whose price didn't change. In this case, PD2 is constant, so the vertical intercept, ME, stays fixed. The line rotates around that point.
Okay, so if PD1 increases, what happens to the horizontal intercept?
ME1 gets smaller, right. You can buy less of good 1 now with the same income. So the budget line pivots inward around the fixed vertical intercept.
And what happens to the slope? P1, PT22. If its PD1 goes up, the slope becomes
steeper. The absolute value P1, P2E2 increases. Good 1 is now relatively more expensive compared to good 2. The market demands a larger sacrifice of good 2 for each unit of good 1.
Okay, steeper inward pivot if P1 rises. What if D fall?
Opposite effect. The horizontal intercept MBO1 increases, you can buy more good 1. The budget line pivots outward around the fixed vertical intercept.
And the slope P1, P22 decreases, so the line becomes
flatter. Good 1 is now relatively cheaper. The market requires less sacrifice of good 2 to get good 1. Understanding these pivots is absolutely key for deriving the demand curve later on.
All right, we've built the 2 essential pieces of the puzzle. We have the consumer's desires mapped out with the indifference map.
Showing what they want, higher curves are better.
And we have their limitations defined by the budget line.
Showing what they can afford, bundles on or below the line.
So now we put them together. The whole point of this theory is to figure out, how does a rational consumer pick the best possible bundle they can actually afford.
Exactly. We're looking for the optimum location. The consumer wants to reach the highest possible indifference curve that is still within their budget set.
Okay, where is that point going to be? We know it can't be inside the budget line, right?
No. Because of monotonic preferences, more is better, any point inside the line is inferior to some point on the line. If you're inside, you're not spending all your income, so you could buy more of at least one good and reach a higher IC by moving out to the line.
So the optimum must lie somewhere on the budget line itself.
It has to. But which point on the line? There are infinitely many points.
It must be the point on the budget line that touches the highest possible indifference curve.
Precisely. It's the point where the budget line is just tangent to an indifference curve. Tangent means they touch at exactly one point without crossing.
And at that specific point of tangency, something special must be true about their slopes, right?
Yes. At the point of tangency, the slope of the indifference curve must be exactly equal to the slope of the budget line.
Okay, wait. The slope of the IC is the MRS.
The consumer's subjective willingness to trade.
And the slope of the BL is the negative of the price ratio.
The market's objective ability to trade.
So at the optimum, the absolute values must be equal.
Bingo! That's the golden rule of consumer equilibrium. The optimal consumption bundle is found where the marginal rate of substitution, MRS, equals the price ratio, P1, P2, 2.
MRS, price ratio. Willingness equals ability. That sounds profound. Let's unpack why this must be true. Why isn't the optimum somewhere else on the budget line where the curve crosses it?
Great question. Let's think about a point on the budget line where the IC is not in tangent, where it crosses the budget line. At such a point, the slopes are not equal. Let's say the MRS is greater than the price ratio.
Okay, so MRS P1, P22. For example, my MRS is 3. I'm willing to give up 3 units of Y for 1 unit of X.
But the price ratio P1, P22 is only 1. The market only requires me to give up 1 unit of Y for 1 unit of X.
What should I do in that situation?
You should definitely make that trade. Your internal valuation of X in terms of Y is much higher than the market's price. You're willing to pay 3Y, but only have to pay 1Y. That's a bargain for you.
Oh, so I should consume more X and less Y.
Yes. By substituting X for Y along the budget line, you can move to a higher indifference curve because the satisfaction you gain from the extra X, valued at 3Y by you, is greater than the satisfaction you lose from the Y you give up, costing only 1Y in the market. You can become better off.
And I'd keep doing that, keep trading Y for X, moving along the budget line.
And as you do that, consuming more X and less Y, your MRS will start to fall because of diminishing MRS. You'll keep adjusting until your MRS drops down and becomes equal to the price ratio.
So any point where MRS is not equal to the price ratio is unstable. There's always an incentive to adjust your consumption.
Exactly. What if it was the other way around? MRS price ratio, say MRS equals 0.5, but price ratio equals 1.
Okay, I'm only willing to give up half a unit of Y for 1X, but the market demands I give up a whole unit of Y.
Would you met that trade?
No way. The market price of X in terms of Y is too high compared to my personal valuation. I'd be better off consuming less X and more Y.
Right. You'd substitute Y for X, moving back along the budget line in the other direction until your MRS rises to meet the price ratio.
So the only point on the budget line where there's no incentive to change, where you're maximizing your utility given your budget, is that single point of tangency, where your internal trade-off rate perfectly matches the market's trade-off rate.
That's the equilibrium. MRS equals P dollars, P to a 2. Maximum satisfaction achieved given the constraints. It's really quite elegant when you see how the preferences and the budget lock together.
Okay, so we found the optimal bundle. That tangency point tells us exactly how much of good 1, 6 but 11, 1, and good 2 the consumer will choose to buy given their income, preferences, and those specific prices.
Right. And if we know the optimal quantity of, say, good 1 chosen at a particular price P dollars, we have 1 point on that consumer's demand curve for good 1.
So to get the whole demand curve, we just need to see how that optimal quantity changes when the price changes.
Exactly. We can derive the demand function, which mathematically shows the relationship between the price of a good and the optimal quantity demanded, $6 of FP, assuming everything else, income, other prices, tastes, stays constant, that ceteris paribus condition.
And the graph of that function is the demand curve, which, as we know from LDMU and now the ICBL analysis, usually slopes downwards.
Let's visualize that derivation again. Remember our budget line pivoting.
Yeah, if the price of good 1 P dollars falls, the budget line pivots outwards, becoming flatter.
Right. It pivots outwards from the vertical intercept. This flatter budget line will now be a tangent to a new, higher indifference curve further out from the origin.
Okay, a new tangency point, let's call it D compared to the old one, C.
Right.
And because D is further to the right on the graph,
it means the optimal quantity demanded of good one has increased. Let's say it went from $XD at the old price to $X2 at the new lower price.
so we have 2 points now. Old price P total 1, old quantity $6, and new price P totalers, new quantity $6. And since P totalers is lower than P totalers and $6 totalers is higher than $6, plotting these points gives us
a downward sloping relationship. That is the demand curve derived from the consumer's optimal choices.
And you mentioned earlier that this negative relationship, the law of demand, is driven by 2 effects working together when a price changes.
Yes, the substitution effect and the income effect. It's really important to understand both.
Okay, let's start with the substitution effect. What's that purely about?
The substitution effect isolates the impact of the change in relative prices alone. When P dollar falls, good one becomes relatively cheaper compared to good two, even if your overall happiness hasn't changed yet. So you naturally substitute towards the cheaper good one, and away from the relatively more expensive one, good two.
So the substitution effect always makes you want to buy more of the good whose price fell.
Always. It always works in the opposite direction to the price change. Price falls, quantity demanded due to substitution rises.
Okay, then what's the income effect?
The income effect looks at the change in your real purchasing power. When the price of a good you buy falls, even if your actual money income hasn't changed, you feel richer because you can now buy the same amount as before and still have money left over. Your real income has increased.
Okay. And how does feeling richer affect demand?
Well, that depends on the type of good. This is where we need to classify goods based on how demand responds to changes in income or real income.
Right. The main category is normal goods, correct?
Correct. For normal goods, when your income goes up, your demand for them also goes up. They move in the same direction. Think better clothes, holidays, maybe higher quality food.
So for a normal good, when the price falls, the substitution effect makes you buy more, and the income effect, feeling richer, also makes you buy more. They work together.
Exactly. That's why the demand curve for normal goods definitely slopes downwards. But what about inferior goods?
Inferior goods. Those are the ones where demand goes down when your income goes up, right?
Precisely. They move in the opposite direction to income. As you get richer, you buy less of them because you switch to better alternatives.
Like maybe switching from instant noodles to fresh pasta, or from taking the bus to buying a car.
Those could be examples, yeah. Basic foodstuff like coarse grains are often cited in developing economies. As income rises, people buy less bajra and more wheat or rice.
So for an inferior good, when its price falls, the substitution effect still makes you want to buy more because it's relatively cheaper.
Correct. Substitution effect is always the same.
But the income effect works in the opposite direction. Feeling richer makes you want to buy less of this inferior good.
Exactly. Now you have the two effects pulling in opposite directions. For most inferior goods, the substitution effect is stronger, so the overall demand still increases when price falls, and the law of demand still holds. The curve still slopes down, just maybe less steeply.
But there's a but coming, isn't there? The weird case.
The weird case. Giffen goods. This is a theoretical curiosity, but important. A Giffen good is a very special type of inferior good where the negative income effect is so incredibly strong that it actually overwhelms the positive substitution effect.
Whoa. So the income effect, buy less when richer price falls, is stronger than the substitution effect. Buy more when price falls. What does that mean for the demand curve?
It means that when the price of a Giffen good falls, the total quantity demanded also falls.
Right.
Or, conversely, if the price rises, quantity demanded rises.
That completely violates the law of demand. The demand curve would slope upwards.
Theoretically, yes. It requires very specific conditions, though. The good must be strongly inferior, and it must make up a very large portion of the consumer's budget, typically in a situation of poverty.
Like the classic potato example during the Irish famine.
That's often cited, though historical evidence is debated. The idea is a family spends almost all their income on basic potatoes and a tiny bit of meat. If the price of potatoes rises dramatically, they become so much poorer in real terms that they can't afford any meat anymore.
So they have to cut out the meat entirely.
And to get enough calories to survive, they have to spend that freed up meat money, plus their original potato money, on buying even more of the now more expensive potatoes. Price rise leads to demand rise.
Fascinating. Highly unlikely in most modern markets, but shows how powerful that income effect could be. Okay, moving away from income effects, what about the price of other goods? How does that affect demand for my good?
That brings us to related goods, which fall into two main categories: complements and substitutes.
Let's start with complements. These are goods used together.
Yes, like printers and ink cartridges, cars and petrol, left shoes and right shoes, you generally consume them jointly.
So what happens to the demand for printers if the price of ink cartridges suddenly doubles?
Well, the total cost of printing goes way up. People will likely buy fewer printers because the complementary good, ink, became so expensive.
So the demand for a good moves in the opposite direction to the price of its complement. Price of ink up, demand for printers down.
Correct. Now, substitutes. These are goods used in place of each other.
Like tea and coffee.
Uh-huh.
Or butter and margarine.
Exactly. If the price of coffee goes up significantly, what are people likely to do?
They'll probably switch to drinking more tea, assuming its price hasn't changed.
Right. So the demand for tea increases when the price of its substitute, coffee, increases.
So for substitutes, demand moves in the same direction as the price of the related good. Price of coffee up, demand for tea up.
You got it. Complements, opposite direction. Substitutes, same direction.
Okay, one last crucial distinction in this section. Movement along the demand curve versus a shift of the entire curve. People mix these up all the time.
They do. It's vital to keep them separate. Think of the demand curve as a fixed path on a map.
Okay, a movement along the curve happens only when?
Only when the price of the good itself changes. If the price of apples changes, we just slide to a different point on the existing apple demand curve. We call this a change in quantity demanded.
So price change of the good itself, movement along the curve, change in quantity demanded. What causes a shift then, when the whole curve moves position?
A shift is caused by a change in any other factor that influences demand besides the good's own price.
Like what?
Like a change in the consumer's income that shifts the curve right for normal goods, left for inferior. Or a change in the price of a related good, shifts right if a substitute's price rises, shifts left if a complement's price rises, or even just a change in tastes or preferences. Maybe a health report says apples prevent cancer.
So if people suddenly want more apples at every possible price because of that health report, the entire demand curve for apples shifts to the right.
Exactly. And we call that a change in demand as opposed to quantity demanded. Own price change movement, other factor change a shift.
Got it. Now, all this analysis has been for one consumer. How do we get to the demand for the whole market?
We get market demand by simply adding up the individual demands of all consumers in that market.
Adding them up. How?
Through a process called horizontal summation. It's quite literal.
Horizontal summation. Explain.
You pick a specific price, say 15 rupees for a kilo of oranges. Then you see how many kilos consumer 1 wants at that price, maybe 2 kilograms. Then you see how many consumer 2 wants at 15 rupees, maybe 3 kilograms. And consumer 3 wants 1 kilogram.
Okay, 2 plus 3 plus 1.
Equals 6 kilograms. So the total market demand at 15 rupees is 6 kilograms. You just add the individual quantities demanded horizontally across the graph at each price level.
That seems simple enough. Is there a catch?
The only small catch is to be careful at high prices where some consumers might demand 0. For example, if consumer 1 stops buying oranges altogether if the price goes above 20 rupees, but consumer 2 keeps buying until the price hits 30 rupees.
Oh, then between 20 and 30 rupees, the market demand is only consumer 2's demand.
Exactly. And below 20 rupees, the market demand is consumer 1's demand plus consumer 2's demand. The market demand curve can have kinks where individual consumers enter or leave the market. You just have to add up who's actually buying at each price.
Okay, we've established that demand curves usually slope down. Price goes up, quantity demanded goes down. But how much does it go down? Is it a tiny drop or a massive plunge?
That's the crucial question for anyone making decisions based on demand businesses setting prices, governments setting taxes. Knowing how responsive demand is to price changes is vital, and that measure of responsiveness is price elasticity of demand, usually written as $.
Elasticity, like a rubber band. How much does it stretch?
That's a great analogy. It measures the sensitivity, the stretchiness of quantity demanded when the price changes.
And how do we calculate it? It's about percentages, right?
Yes, specifically, it's the percentage change in quantity demanded divided by the percentage change in price.
Okay, so DOED equals delta QD, equal delta P. And we usually look at the absolute value, ignore the negative sign.
Generally, yes, for simplicity, since it's almost always negative anyway due to the law of demand. So if the price of bananas goes up by 40%, say from 5 rupees to 7 rupees.
Okay, 40% price increase.
And a quantity demanded falls by 20%, say from 15 bananas to 12 bananas.
20% quantity decrease.
Then the elasticity dollars would be 20%, 40%, which equals 0.5.
0.5. Okay, so what does that number tell us?
That number is key. It allows us to classify demand into 3 main categories based on how responsive it is. Since 0.5 is less than 1, this demand is inelastic.
Inelastic, EOA to 1 atom.
Meaning demand is not very responsive to price changes. The percentage change in quantity was smaller than the percentage change in price. 20% is less than 40%.
And what kinds of goods tend to have inelastic demand?
Usually necessities, things you really need and that don't have many close substitutes. Think basic food staples like salt or rice, essential medicines, maybe petrol for car owners in the short run. Even if the price jumps, you still have to buy almost the same amount.
Okay, that makes sense. What's the second category?
Elastic demand, tin 25. Here, demand is very responsive to price changes. The percentage change in quantity is greater than the percentage change in price.
So if the price of, say, a specific brand of luxury chocolate goes up by 10%,
and the quantity demanded plummets by, say, 25%.
then the elasticity is 25%, 10%, 2 hives and 5 sons. Since 2.5 is greater than 1, demand is elastic.
Exactly. People react strongly to the price change, likely because it's a luxury good, or because there are many other chocolates they can easily switch to.
Makes sense. Luxury items or things with lots of substitutes tend to be elastic. What's the middle ground?
Unitary elastic demand, 11.8 to 1.1. This is where the percentage change in quantity demanded is exactly equal to the percentage change in price. If price goes up 10%, quantity falls by exactly 10%. The elasticity is precisely 1.
Okay. Inelastic, less than 1. Elastic, greater than 1. Unitary, exactly 1. Now, does elasticity stay the same all along a typical demand curve? Like a straight line demand curve?
Great question, and a common misconception. No, for a standard linear straight line demand curve, the elasticity is actually different at every single point.
Really? Even though the slope is constant, how does that work?
Remember the formula. It's percentage change in Q divided by percentage change in P. While the slope, delta P, delta Q, is constant, the base values of P and Q are changing as you move along the line. This changes the percentage calculations.
Okay, so where is it elastic and where is it inelastic on that straight line?
At the top part of the demand curve, near the vertical price axis where price is high and quantity is low, demand is elastic. ED 2021. It's actually infinitely elastic right where it hits the price axis. 2 days.
High prices, elastic demand. What about the bottom part?
Down at the bottom part, near the horizontal quantity axis, where price is low and quantity is high, demand is inelastic. EDD rotor, and it's perfectly elastic right where it hits the quantity axis.
And the midpoint, where is it unitary elastic?
Exactly. At the midpoint of the linear demand curve, the elasticity is precisely 1. EDD all 1, 1.
Wow. So a firm selling a product with a linear demand curve needs to know where on the curve they're operating because the responsiveness changes.
Absolutely critical. The pricing strategy should be different depending on whether you're on the elastic or inelastic portion.
Are there demand curves that do have constant elasticity all along them?
Yes, there are specific shapes for those. A perfectly inelastic demand curve is a completely vertical line. Quantity demanded is fixed no matter the price.
Like maybe life-saving insulin for a diabetic. They need a certain amount regardless of price.
That's the classic example, yes. Then a perfectly elastic demand curve is a completely horizontal line. At that specific price, consumers will buy any amount, but if the price rises even slightly, demand drops to 0. This applies more to perfectly competitive firms.
Okay, and the unitary elastic one, ED $1 everywhere.
That shape is a specific curve called a rectangular hyperbola. Its defining feature is that price times quantity, times Q, is always the same constant value at every point on the curve.
That's the total amount spent by consumers, or the total revenue for the seller, right?
Exactly. Which leads us nicely into the factors determining elasticity and its relationship with expenditure.
Right. What makes a good more elastic or inelastic in the real world? We mentioned nature of the good necessities versus luxuries.
Necessities tend to be inelastic. Luxuries tend to be elastic. That's a major factor.
And the other big one?
Probably the most important one, the availability of substitutes.
Ah, yes. If there are lots of good substitutes available,
then demand will be highly elastic. If the price of one brand of petrol goes up, but others don't, you'll just switch brands easily. But if the price of all petrol goes up and you need to drive, the demand is more inelastic because switching to electric cars, public transport, is harder or takes time.
So fewer substitutes means more inelastic demand? Many substitutes means more elastic demand.
Generally, yes. Also, the proportion of income spent on the good matters and the time period considered. Demand tends to become more elastic over time as people find substitutes.
Okay, let's connect this directly to that total expenditure or total revenue,
Yeah.
total times Q to LT. How does elasticity affect whether total spending goes up or down when the price changes? This is huge for businesses.
It's fundamental. Let's summarize the rules. If demand for your product is elastic,
Meaning quantity is very responsive.
then price and total expenditure times Q bouts move in opposite directions. If you raise your price, the quantity demanded falls by a larger percentage, so your total revenue actually goes down.
So if you sell an elastic good, you should consider lowering the price to increase total revenue.
Correct. The increase in quantity sold will more than make up for the lower price per unit.
Okay. What if demand is inelastic?
Quantity is not very responsive.
Then price and total expenditure move in the same direction. If you raise your price, quantity demanded falls, but only by a smaller percentage. So the higher price effect dominates, and your total revenue goes up. This is why governments love taxing inelastic goods like cigarettes or alcohol, right? Raising the price tax brings in more revenue because demand doesn't fall much.
Exactly. And it's why businesses selling necessities might raise prices knowing revenue will likely increase.
And the last case, unitary elastic do collapse.
Here, the percentage change in price is perfectly matched by the percentage change in quantity. So if you change the price, the total expenditure times Q remains exactly the same. The price effect and quantity effect perfectly cancel each other out. #tag outro.
Wow. Okay, that was quite the journey, wasn't it? From simply asking, why do we choose this? All the way through utils, indifference curves, budget lines, tangency, and elasticity.
It really covers the core logic of how economists model individual choice under scarcity.
I think the big takeaway for me is seeing consumer behavior as this constant, really precise balancing act. It's your internal desires, your indifference map.
Colliding with the external reality of your budget line, your limited resources.
In that sweet spot, the optimal choice happens right where those two forces perfectly align, where your personal willingness to trade, the MRS.
Exactly equals the market's rate of trade, the price ratio. It's quite beautiful, mathematically and conceptually.
And from that optimal choice, we get demand. And understanding demand isn't just about drawing a curve. It's about understanding the income and substitution effects, and crucially, measuring the responsiveness with elasticity.
Absolutely. That concept of elasticity, knowing whether demand is elastic or inelastic, that's practical, powerful knowledge for anyone in business or involved in policymaking. It dictates pricing strategies, tax impacts, and so much more.
So as a final thought for everyone listening, here's a little challenge. Start looking at your own choices through this lens.
Yeah, become your own economist.
Think about the last few things you bought. Were they necessities or luxuries? Do they have many substitutes? Would you classify your demand for them as elastic or inelastic?
And maybe take it a step further. Think about complements. You mentioned smartphones earlier. Is your demand for the phone itself elastic or inelastic? What about the demand for the mobile data plan you need to use it?
Good one. Are they likely to have the same elasticity? Why or why not?
Keep applying these ideas. Economics is happening all around you in every decision you make. We hope this deep dive has given you the tools to see it more clearly.
We are proud educators from School on X, and it's been a pleasure exploring the theory of consumer behavior with you.
We look forward to our next deep dive. Keep thinking like an economist.
See you next time.